All right, this is the second part of the review for quiz 2526. And it says, first they give us a velocity equation. When is the particle moving to the right? Particle is moving to the right when our velocity is positive. This is the velocity, and this is positive when it's above the x-axis, which is between C and E. When does the particle's speed appear to be at its maximum? So speed is not positive or negative, it's just the absolute value. So if you were to look, we see that we hit a top speed in the negative direction here and a top positive speed here. And if you had to compare the two, this looks like a greater value than that does. So I would say at B is when we're at our top speed. That's also when we're at our minimum velocity, because again, velocity can have a positive, negative to it, but the speed would just be the absolute value. When is the particle at rest? We're going to be at rest when our velocity equals 0. This is the velocity, and it's 0 at A, C, E, and G. When does the particle change direction? That's when the velocity is 0 and v of t changes signs. When it's negative, it's moving to the left. When velocity is positive, it moves to the right. So when we look, A is where it's 0, but it was negative before, negative after, so velocity didn't change sign. We don't change directions there. We do, however, change direction at C, because velocity goes from negative to positive, and at E, because velocity goes from positive to negative, but not at G, because we don't know what's going on past that. So just C and E. And when is the particle's speed decreasing? When velocity is moving towards 0 would be a good way to say it, or when velocity and acceleration have opposite signs. So both are correct ways of kind of thinking about this. Now if I'm looking initially, I have this speed here and I'm moving towards 0. So from 0 to A, my speed is decreasing because I'm moving towards 0. From A to B, I'm moving away from 0, so speed is increasing. But then B to C, I'm moving towards 0 again, so B to C. From C to D, I'm moving away from 0, so speed is increasing. But from D to E, we're moving back towards 0. E to F, moving away, speed is increasing. From F to G, moving towards, speed's decreasing. So these are the 4 places where our speed would be decreasing. Then we're given the area of a circle formula, and we're supposed to find dA dt, the change in the area with respect to time. So just a generic, we aren't given a specific radius, just what would that be? So the change in area with respect to the change in time would be pi times the derivative of r squared. So that's going to start off as 2r, so we'll bring the 2 in front with that, okay, times the derivative of r, which is dr dt. So that would be our derivative of the area formula with respect to time. So now 13 says a ripple in the water creates a circle with expanding radius. At the moment that the circle has a radius of 10, the area is growing at a rate of 40 pi inches per. So this is dA dt, the change in area, and 10 inches is the actual radius. At what rate is the radius expanding? So what they're asking for is dr dt. How fast is that going? So we have our formula up here. Let's put these things in. We're going to have 40 pi equals 2 pi times the radius 10 times dr dt. Okay, so this is going to be 40 pi divided by 20 pi, which will give us 2. And that's 2 inches per second using the units that are available. Again, it's 40 pi divided by 20 pi, and that's where the 2 comes from. Okay. So now it says if the radius expands at the rate from problem number 13 constantly. So let's say now it's a constant 2 inches per second. What is the rate that the circumference is expanding? So now we need a circumference formula, and they give it to us right there. So let's take the derivative of that. dc dt is equal to 2 pi times dr dt. All right, and we just said dr dt was 2, so if you put that in, dc dt is equal to 2 times pi times 2, which is 4 pi. Circumference is a linear measure, It's the distance, so it'll just be inches per second, not inches squared or inches cubed or anything like that. All right, and then we've got a 20-foot ladder resting against the side of a house, and it begins to slide away from the house. At the moment that the base of the ladder is 10 feet from the house, the top of the ladder is dropping at a rate of 2 feet per second. So let's get a visual on this. Got our ladder right here. It's a 20-foot ladder. It's falling down the house at a rate of 2 feet per second at the moment that it's 10 feet away down here. Okay, how fast is the base of the ladder moving away from the house at that same moment? So we're trying to figure out how this is changing. So a couple things we might need. One is we might need this side here. So we'll call this x, and we'll call this y. So x squared plus 10 squared equals 20 squared. If you do that, you'll get x squared equal to 300, so x is equal to the square root of 300. All right, so that's that side. And then we also need a relationship that we can take the derivative of. So since x and y are both changing, they have to be variables, but the 20 will always be 20 in this. It never changes, so it can keep it at 20. Now take the derivative. 2x times dx dt plus 2y times dy dt equals derivative of 20 squared, which is 0. Okay, so now x we said was square root of 300, so 2 times square root of 300 times dx dt, which is 2 feet per second. And technically it's negative because it's getting shorter, so I'm going to put in a negative 2 there. Right? Plus 2 times y, which is 10, times dy dt, which is what we're trying to find, equals 0. All right, so this is going to be negative 4 square roots of 300. If we move that over, we get 4 square roots of 300 equals 20 dy dt. So dy dt is equal to 4 square roots of 300 divided by 20, which, if we do that real quick, 4 square roots of 300 divided by 20 gives me 3.464 feet per second. Okay. So it's moving faster down here than it is at the top, is what we're seeing. Okay. Now, B says, if the top of the ladder falls at a constant rate, will the base be traveling faster, slower, or the same speed when it's 15 feet from the house versus then when it was 10? So now what they're asking is same setup, but now let's make this 15 instead of thing. This is still falling at 2 feet per second. We want to know, is this now faster or slower than the 3.464? So if we do another x squared plus 15 squared equals 20 squared, we're going to get x equal to 400 minus 225. That's 175. So this will be the square root of 175 now. Everything else down here, that we don't have to redo the derivative. We can just use this rule line right there. So 2 times x, which is the square root of 175, times dx dt, which is negative 2, plus 2 times y, which is 15 now, times dy dt equals 0. So this is our equation with the new information in it. And this is negative 4. If we move that over, we're going to get dy dt equal to 4 square roots of 175 over 30. And if we do that, 4 times the square root of 175 divided by 30, we get 1.764 feet per second. Okay, so it's actually moving slower now.